So the electron energy and its position are complementary. Remember, kinetic energy is 1/2 mass times the velocity squared. So the energy is proportional to the velocity. We can't know the position and the velocity at the same time. We can't know the position and the energy at the same time. We can measure the energy from the line spectra. So we can identify the energy of that photon, which tells us the energy difference in the electrons. But the best we can do is to describe its position is to say, well, there's this region that it's probably within. Just like we had the circles with the pitching the electrons. There's a volume that the electron is likely to be in at any given time. This is called an orbital. Now, the word orbital is similar to the word orbit, but it's not the same thing. An orbit is like the Earth going around the sun. It's a fixed path. It's predictable. It's Newtonian. An orbital is a distribution map showing where the electron is likely to be. It's hard to get your mind around. Many of the properties of atoms are related to the energies of the electrons, and that's why we care about the electrons, at least in general chem. Okay, we heard about Schrödinger's cat. Well, Schrödinger came up with an equation that allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location in the atom. Now, this is not a nice little equation like y equals mx plus b or anything like that. We've got these wave functions. This is the Greek letter psi. So the wave functions describe the wave-like nature of the electron. And if we plot y squared, those wave functions squared, we can get an orbital, a volume. Okay. The math here is just horrible. That's just a very, very simplified, this function is equal to that function, and that's as far as we're going to go with that. There are 3 integers that are in the wave function. So think of them as variables. And they're n, l, m sub l, and m sub s. You plug these different numbers into the big old hairy equation, and you get different orbitals. These were put into the equation because we know that the energy of electrons is quantized. It's only fixed levels, and so that's why these numbers got put in there. These are called quantum numbers. They're put in to quantize the wave function. So n is the principal quantum number, L is the angular momentum quantum number, m sub L is the magnetic quantum number, and then there's another one, the spin quantum number. So this first one is an integer that describes the overall size and the overall energy of an orbital. This corresponds to the energy levels, the different orbits in Bohr's model. And so this is where Bohr's model can kind of help us visualize what's going on here. So n can be any integer greater than or equal to 1. 1, 2, 3, 4, 5. Okay, so if you have a higher n, you have higher energy. So an electron with n equals 3 has higher energy than with n equals 2. You can think of it as being in a larger orbit. The larger the orbit, the bigger the energy. They're not in orbits, but it's easier to think of it that way. We can calculate the energy of it for hydrogen. So the energy for an electron is equal to minus 2.18 times 10 to the minus 18th joules times 1 over n squared, where n is that principal quantum number. The energy is negative because the electron's energy is lowered by its interaction with the nucleus. If that doesn't make sense to you, just be okay with it being negative. You don't necessarily have to understand that too much. As n gets larger, the difference in energy between each orbitals gets smaller. So as n gets bigger, going from energy level 1 to energy level 2 to 3, they get closer and closer together. So here's kind of a visual of that. So energy increasing this way. So here's energy level 1, principal quantum number, n equals 1. So here's the energy of an electron in that orbital. N equals 2. You see this energy is significantly higher. And we go to n equals 3 and n equals 4. And we see that the difference in energy is getting smaller and smaller as we go up. The angular momentum number describes the shape of the orbital. And L can have integer values from 0 to 1 less than n. So if L equals 0, that corresponds to an orbital that's also given a letter designation of S. L equals 1 corresponds to P, L equals 2 to D, and L equals 3 to F. Does that seem random? No? Well, I'm glad it doesn't seem random to you. It seems random to most students. The SPDF business, what the heck? This has to do with terms that were originally used to describe the lines in the spectrum. I always forget what S is, but P is principal, D is diffuse, and F is fine. And it just described qualities of the lines. And people were familiar with using them, and so they kept them along. Just a little history of S, P, D, and F. We mostly just need to remember them.
Just those ones.
Pardon me?
Just those, the ones right there.
S, P, D, and F. Yeah, we won't deal with anything larger than that. The magnetic quantum number tells the orientation of the orbital. So if you think of three-dimensional space, you can have things oriented differently, right side up or sideways, etc. The values for this number vary from minus L to plus L and include 0. So if L equals 2, then M sub L could be minus 2, minus 1, 0, plus 1, or plus 2. So that tells us there's 5 different orbitals that have L equals 2. I don't enjoy lecturing on this. It's hard to explain. So the spin quantum number talks about the spin of the electron. This is a fundamental property of an electron. All electrons have the same amount of spin, but they have an opposite orientation of the spin. So atoms are not spinning like tops, but let's think of them that way because it's easier. So if you think of something spinning, do you guys know what Beyblades are? My little guy's into Beyblades. They're these little tops, right? And you battle with them. And so a top can spin clockwise as you look down on it or counterclockwise, right? So we'll just call one plus and one minus. They have the same amount of spin. We call them plus 1/2 and minus 1/2. We don't need to know why. I can't remember why. It's just plus 1/2 or minus 1/2. So electrons have spin. So when we describe an orbital, we use these 4 quantum numbers to describe an orbital. Those numbers would be put into the equation to calculate the shape and the energy of it. We're not going to deal with that, but we are going to look at these 4 numbers. So each combination of the first 3 describes one orbital. So for example, n equals 1, L equals 0, M sub L equals 0 describes a particular orbital. It describes the 1s orbital. There can be multiple orbitals with the same value of n. They're said to be in the same principal level or the same principal shell. They are in the ballpark of the same energy. And then orbitals that have the same n and L are said to be in the same sublevel. Okay. What was I going to do there? Oh, it's a blank slide, yes, because I need space to draw a picture. I think I was going to talk to you about the Quantum Hotel, a discount resort for electrons. Okay, so if you've ever been to Las Vegas, you know that they have some pretty funky looking architecture in those casinos. This one I don't think you could actually build because it's an inverted half pyramid and it would tip over, but it's a picture, so we can do this. So think of this as a hotel in Las Vegas, and there are different floors. So here's the first floor, and the second floor, and the third floor, and the fourth floor. So these levels correspond to principal energy levels. As you go up, I didn't do it super clearly, but as you go up, the floors get closer and closer together. So if n equals 1, maybe we can do this over here. So here's n. If n is 1, what are the possible values for L? L can be 0 up to 1 less than L.
Plus 1, 0, and negative 1?
Well, that's the next one. This one, the only possibility is 0. Because it can go between 0 and n minus 1. Well, n minus 1 is 0, there's only 1. And so there's one orbital. I'm gonna draw it as a box. There's one orbital on the first floor. L equals 0 corresponds to the letter S. So this is the S room. It's on the first floor, and so we call it 1S. On the second floor, so principal energy level 2, what are the possibilities for L? It starts at 0 and goes up to 1 less than n. 0 and 1. So we could have 0, that's S, or we could have 1, SP, dF. So on the second, we've got two different shells, or sublevels. We've got the S and we've got the P. On the third floor, we can have 0, we can have 1, and now we can also have 2, and that's D. So up here we have 3 sublevels. So there's 3S, 3P, 3D. And in my quantum hotel, those would correspond to rooms. You know, rooms in the hotel, some of them are bigger than others. Okay? How many sublevels would be on level 4? 4. Yeah. So look at this. First level, 1 sublevel. Second level, 2 sublevels. Third level, 3 sublevels. Fourth level, 4 sublevels. Guess how many on the 7th? 7. Okay? It's just the same number, right? Well, then we had m sub L, right? So if L equals 0, then m sub L is minus L to plus L, including 0, so m sub L has to be 0. So that corresponds to a particular orbital. In the hotel, that corresponds to a particular bed, okay? So in this S room, where L is 0, how many values for m sub L do we have? Just 1. It has to be 0. Now, when L equals 1, what are the possibilities for m sub L? Minus 1, 0, and plus 1. Now we've got 3. The P room has 3 beds. Each orbital is a bed. What if L equals 2? Now we've got -2, -1, 0, +1, +2, 5. Have you ever seen a hotel room with 5 beds? Me neither. That doesn't matter. This is an imaginary hotel. We can have it be whatever we want it to be. So I'm just going to put little boxes here. So the S room has 1 orbital. Sorry, don't mix my metaphors here. The S room has 1 bed. The S subshell, sublevel, has 1 orbital. The P sublevel has 3 different orbitals. The D sublevel has 5. So the number of things goes 1, 3, 5, and the next one would be 7. They're odd numbers increasing. Yes?
So the N will be the shell.
N is the shell or principal energy level.
The SEEF is the subshell.
Those are the subshells or sublevels. Yeah. So on this second level, there's 2 different sublevels. The level is divided into 2 slightly different parts. And for n equals 3, there's 3 different sublevels within that one level.
And then the ML will be
M sub L is,
the orbital, number of orbitals.
it's the orbital orientation. So L describes the shape of the orbital, and M sub L describes the orientation. Yeah, we'll get to that. We'll get to some pictures in a minute, the actual shapes, and then I think you'll be able to see it a little better.
Okay. So the N will be the floor. The L is the room, and then M sub L will be the bed.
Yeah, so N equals the floor of the hotel, and L equals the particular room, and M sub L corresponds to a bed. And then the spin quantum number, M sub S, okay, so this is, I think of electrons as being masculine. I don't know why. So the electrons are guys. They're all going to this convention or something. They're staying in the same hotel, and they're having to share beds. Do guys like to share hotel beds? No, not generally. Not with other guys that they don't know, right? That's just like creepy, right, guys? Yeah. So what they do, so if this is the bed, here's the pillows. So we've got one guy sleeping right side up in the bed, and the other guy, they won't let you sleep on the floor, or they do that. The other guy sleeps upside down in the bed. It's like, we're going to avoid any appearance of anything going on here, and so they sleep head to toe. So this guy is the +1/2 spin, and this is -1/2. He's upside down. Okay?
But how do we know when it is plus and when it is minus?
Well, the ironic thing is they can actually flip their spins. But when we talk about putting putting electrons into these orbitals, by convention we say that they're going to be positive spin before their negative spin. We'll get to that in a minute as well. Okay, so this is maybe a little bit hazy, but let's go on. So I kind of already covered it, but here it is in a prettier form. So in N equals L, the first energy level, L can only be 0, so we have 1 S subshell, and then in that orbital there's only a single orbital. On the second principal energy level, we have 2 different sublevels, S and P. For S, we only have a single orbital, and for P, there are 3 orbitals. In the third energy level, third principal level, we've got 3 different sublevels, S, P, and D. And the D orbital, the D sublevel has 5 different orbitals. Okay, so we should be able to do things like this. List the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? Well, what does 5D tell us? That gives us 2 of the numbers. What is N?
5.
N is 5. And, L is what? Think S, P, D, 0, 1, 2. So L is 2. Well, if L is 2, what can M sub L be? Minus 2, minus 1, 0, plus 1, and plus 2. So how many orbitals are there in that 5D? There's 5. 5 orbitals. Now, if they asked you to write the sets of quantum numbers for each of those, like, well, this is tedious, but you'd have 5. They'd all be 5 and 2, and one's negative 2. 5, 2, negative 1. 5, 2, 0. 5, 2, plus 1. 5, 2, plus 2. It's not unlike the numbering of many buildings, the rooms. We are on the 2nd floor, and so our room number is 240. The 2 tells us what floor we're on, right? And on the chemistry building, the classrooms, there's 200, there's 220, 230, 240, 250, 260, 270, right? So the 2nd digit tells you which room. Now, we don't have a designation maybe for which bench you're at or anything like that, but it's the same kind of idea. So this one might be, 5, this is 5, 2, minus 2. That describes a particular place, a particular kind of environment for an electron. Any questions? Yes?
What is the main number?
So this is N, and this is L, and this is M sub L. So this describes one orbital, and this describes another orbital, and another, and another, and another. So these are the 5 orbitals.
Wait, so why is L2 and not 4?
Why is L2 and not 4? Because it's D. So L can be 0 up to minus 1 minus N. So for the 5th level, L could be 0, 1, 2, 3, or 4. All of them are possibilities. The letters, 0 is S, P, D, F. I think the next one would be G, but we never go there. Okay? Good question. Yes? What about MS? Okay, so what we'll find is that each electron has a unique set of quantum numbers. And in this orbital, we can have 2 electrons, one with a plus spin and one with a negative spin. So the first 3 quantum numbers can be the same for 2 electrons, but then the second one, the last number will be different. So we don't know what they are. Any other questions? So get this. Each set of quantum numbers is supposed to specify an orbital. However, each set contains one quantum number that is not allowed. Replace the quantum number that is not allowed with one that is allowed. So, for A, N equals 3, L equals 3, and M sub L equals plus 2. Which one is not possible? L. L can only go up to 1 less than N, so it can't be 3. What could we replace it with? 2. Could we replace it with 1? If we replace this with 1, then M sub L can't be plus 2. Okay? Let's look at this one. N equals 2, L equals 1. Could we have L equals 1 with N equals 2? Yeah. M sub L is minus 2. Does that work with this guy? No. So what would work? Minus 1. because m sub L can be minus L up to plus L, including 0. How about this last one? L has to be 0. Any questions? It's strange, huh? Okay, so now we're going to try to explain atomic spectroscopy. So each wavelength, each line of light that we see, corresponds to an electron transitioning between orbitals. When an atom absorbs the energy, the electron takes that energy and jumps up to a higher energy orbital. So in my quantum hotel analogy, energy is money. Energy is money a lot for me. So what happens is, maybe that orbital was playing the slots and won some money, and so he's going to pay to be in a more expensive room higher up in the hotel. That's an excited state. He's happy about that. He's excited about it. But that excited state is unstable. He can't sustain that, and the electron is going to relax, go back down to a lower energy level. When that happens, the energy difference there is emitted as a photon of light. And that photon of light has energy that's equal to the energy difference between the orbital levels. So here we have an electron that was in principal level 1. It absorbs energy and makes this quantum leap up to n equals 3. So this absorption of energy has a specific amount. You have to have exactly the right amount of energy. It's like exact change on a bus, right? You have to have the exact fare. They're not going to let you put in more, and they're not going to give you change or anything. Exact change only. So it goes up there. That would correspond to a dark line in the absorption spectrum, because electrons can absorb that particular level of energy and go up here. Up there, it's not stable. It's going to come back down. It doesn't necessarily go down to where it started from. It could go down to any other levels in between. And when it does, the difference in energy, the energy that it's losing, is emitted as a photon of light. This photon has a particular energy which corresponds to a specific wavelength, and those are the individual lines we see. Any questions? Some of that other stuff is really kind of confusing and all. I think this is really, really cool. You don't have to agree with it. So when we're transitioning to a higher energy state, the electron has to get the correct amount of energy. Electrons in the higher energy states are unstable. They tend to lose and transition to lower energy states. There's another glitch in my PowerPoint slide. So each line in that spectrum, emission spectrum, corresponds to the difference in energy between two energy states for the electrons in that atom. We can predict the wavelengths of lines in the emission spectrum for hydrogen. We can calculate the difference in energy between any two states. So for an electron in energy state n, there are n-1 energy states it can transition to. So it can generate n-1 lines. Why can't it generate n lines? It can't go below itself. It can only go above. So both the Bohr and the quantum mechanical models predict those lines really well for a one-electron system, which is hydrogen. So we will look at hydrogen. So the energy of a photon released is the difference in energy between the two levels. So delta E, the energy that's released, is the final energy minus the initial energy. And we learned earlier that for an electron in an energy level, energy is minus 2.18 times 10 to the minus 18th times 1 over n squared. So it's the final level, whatever that is, and then we're going to subtract that with 1 over n, where this is the initial energy level. When we combine those terms, we get this equation. So the change in energy minus 2.18 times 10 to the minus 18th joules times 1 over the final level squared minus 1 over the initial level squared. And two other things we need to remember. The change in energy for the atom is equal to, but opposite in sign, to the change in energy, the energy of the photon. Because the energy is being lost by the atom, gained by the photon. And then we also need to remember this one, the wavelength equals hc over E. That is just a rearrangement of E equals hc over lambda. The energy and the wavelength are inversely related. Okay, so this is an illustration of some energy transitions for the hydrogen atom. So in its ground state, hydrogen's 1 electron is in this n equals 1 level. If you give it enough energy, if you really zap it, you can increase that to n equals infinity, which is essentially taking the electron off of the atom. That's ionizing it. But if you don't go quite that high, maybe it's starting at n equals 5, it can transition back down to n equals 1 from any of these levels. I said something wrong earlier, but I don't think it's going to matter, so I'm not going to correct it. These have quite a high energy. You see the length of the line is corresponding to energy. These are in the ultraviolet region. We can't see them with our eyes. Going from 5, 4, or 3 down to 2, these energies are smaller and they fall within the region of the visible spectrum. And so those are the 3 lines that we can see. And then there are also some that are infrared wavelengths that are smaller yet. Any questions? You don't need to remember these specific numbers or colors or anything. Just the idea. Okay, so determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So it's helpful to draw a picture, little diagram here. So we're starting with, we've got n equals 2 and we've got n equals 7. I'm not going to draw the other ones because it's just going to make things confusing. So it's transitioning from n equals 2 to n equals 7. And this is energy increasing as we go up on this little diagram. Well, the change in energy is equal to minus 2.18. And I will give you this equation if you need it on a test. Joules times 1 over nf squared minus 1 over ni squared. What we need to know is the final level and the initial level. Which one's the initial level? N equals 2. So n initial is 2. And this is the final. N final equals 7. One of the hardest things about this is communicating correctly with your calculator. So this is going to be 1 over 7 squared minus 1 over 2 squared. And it's probably easiest to say, okay, well, I know that's 1 over 49 minus 1 over 4. So on my calculator, I'm going to put in negative 2.18 EE minus 18 times the quantity. I'm going to use parentheses. And I'm going to do 1 divided by 49 minus 1 divided by 4, and I'm going to close the parentheses and press equals. So the change in energy equals positive 5.01 times 10 to the minus 19 joules. So that's the energy. But we want the wavelength, right? This is the difference in energy between those two levels. That corresponds to the energy of the photon. The wavelength equals hc over E. So we've got h. Joule seconds. And we've got c, speed of light. And then we've got our energy in the bottom here. This would be pretty tough if you didn't know how to use the scientific notation function on your calculator. What are the units going to work out to? Meters. So joules cancel joules, seconds cancel seconds, I'm left with meters. Okay, so 6.626 times 10 to the minus 34 times 3 EE8 divided by 5.01 EE minus 19. So the wavelength is 3.97 times 10 to the minus 7 meters. Any questions? Is that visible light? I don't think so. So I'm familiar with visible light being expressed with wavelengths in nanometers, and it's like 400 to 700-ish. So if I want to put this into nanometers, I am going to multiply by 1 times 10 to the 9, or divide by 1 times 10 to the minus 9. I'm getting 397 nanometers. So that's just like right on the edge, right? Probably couldn't see that. Maybe some people could. Maybe dogs could. I don't know. But a little below. Any questions?